In life, we learn that at times a series of ordinary events leads to something wonderful. Nature often works the same way. This is the story of a sequence of geologic events that formed a rather ordinary layer of rock that has had and continues to have a profound impact on our own history and is the key to the well-being of millions of birds.
Hello, I'm Myron Cook. I'm sure glad to be here with you today. And I am between Laramie and Cheyenne, Wyoming, standing next to, yes, an unbelievably important layer of rock. Now I know there are going to be some of you out there thinking, well, this is not an especially interesting looking layer of rock, at least from a distance, and even up close it's not super uncommon. How could it be so important, Myron? Maybe you've overdone it this time, and I don't think so. So I hope I've caught your interest here. And we want to take a look at this rock and then look at the bigger picture and put it together and learn how it has changed history. It made history. Coming right in close to the rock, oh, look at these beautiful small pebbles. They're pretty angular. It's obviously granite, isn't it? You'd like to have a lot of this to put maybe in your yard in a rock area. Just really nice, not very well rounded. The clasts are of different sizes. We see that they're set in a matrix, or the material that in between the clasts is very light colored. It looks like some of it's sandstone, small sand grains. And there's some other material in here too that we'll be learning about. The clasts vary dramatically in size. Here's some here quite a bit larger that we see. That's a really nice clast, isn't it? Of granite, all granite here, dominated by granite. And if we look further down, well, they're getting bigger. Larger clasts here. Oh, and look at this dark colored one. Here's some that has a little darker coloring to it. And if you get the dark colored clast, it turns out it's a very special rock named Anorthosite.
A nice example of foresets, also known as crossbedding. Here are some typical examples of the consolidated pebble conglomerate.
I know that there are a lot of you out there that are already thinking about gold. And why would that be? Those of you that know gold are seeing this granite, all this granite in here, these deposits of granite, and thinking, I know gold is associated with granite. Maybe we have some placer gold here in these ancient river deposits or something. Boy, that's a good idea. That's a really good thought. But it turns out there's not much gold here, so we've got to keep going and learning.
Now a word about the darker colored anorthosite. It's a rock composed of primarily plagioclase with some pyroxene, ilmenite, magnetite, olivine, and some others can be in there, and is common on the moon. Sometimes it is a pure calcium-rich plagioclase, which is an aluminum silicate named labradorite. Wow, is it beautiful! And it is found in the Laramie Mountains.
Some of you may be aware that recently mining anorthosite in Greenland has been touted as a green alternative for producing aluminum. Could it be that the Laramie Mountains anorthosite could be mined to produce aluminum?
Well, during World War II, the U.S. government thought it needed its own source of aluminum. So in 1944, they built a factory to extract aluminum from anorthosite near Laramie, and then the war ended and it was never used. Of course, a broader perspective is always good to have, and the drone can certainly help us with that. The ridge I'm standing on is about halfway up through the formation. The material above me is largely made of unconsolidated sand, gravel, and cobbles. The total thickness of the unit is about 300 feet here. The age of this unit ranges from about 15 million years to 5 million years ago, which is Miocene age. The top of these deposits forms a great plateau that stretches far to the east into the Great Plains. Wow, what a view!
Wandering around looking at this unit, I've seen some pretty large clasts, but here where they're weathering out here, they seem to be all over at this level, a little higher up. Let's take a look at what I'm seeing.
We're seeing large cobbles and even boulders of granite and anorthosite. Pretty amazing.
If you think about where you've seen large clasts and river systems, they're always close to mountains, aren't they? And in fact, there are some right behind me. Let's take a look.
This Google Earth view is looking onto the plateau and out into the plains to the east, similar to what we saw from the drone. I've been showing you the outcrop from this area. With a simple rotation of 180 degrees, we look to the west and see the low-relief Laramie Mountains. They are the source of all the material we've been observing on the outcrop and beyond in the plateau areas. Backing out, we see a much larger perspective looking to the south. The Laramie Mountains formed during the Laramide orogeny about 65 million years ago and has been deeply eroded, exposing a lot of basement rock in the core. Only on the very edges do we see sedimentary rocks. The dashed line shows the general shape of the Great Fold before erosion, which removed some 20,000 feet of rock. The southern Precambrian core is dominated by the 1.4 billion-year-old Sherman granite, and in the northern areas shown here is the general location of the 1.7 billion-year-old Anorthosite complex. As the mountains eroded, they created great fans or aprons of clastic material that extended out into the plains. And at about 5 million years ago, these aprons began to be eroded, and it continues today. The long valley centered on this line is part of that erosion, and there are a series of valleys cut into the apron by small rivers extending out into the plains shown by the arrows. Geologists like to use modern analogs to help them understand how the world looked in the past. I like to think of the Mojave Desert as an analog for our study area before the erosion of the last 5 million years. The hot and dry climate of the Mojave is not a good climate analog because the Miocene time was cool and quite dry with grasslands covering much of the area. However, the Mojave is a good analog for the geologic processes. We see mountain remnants drowning in a sea of sand, pebbles, and cobbles that have eroded from the mountains. In some areas, only the very tops of the mountains poke through the great aprons of alluvium, which are being deposited in alluvial fans and ephemeral or intermittent rivers. Imagine some grasslands here, and you'll have a pretty good image of Miocene time on the high plains.
Well, I'm sure having fun with this one because I'm throwing you some curveballs. I know there are a lot of you out there asking, why, Myron? Why are you showing us an interstate highway with a train going up a railroad track? And what does that have to do with this special rock or this layer of rock you've been showing us? Well, it turns out that that layer of rock is the surface upon which that interstate and that railroad track goes up. And that railroad track has special significance because it is the Transcontinental Railway. Yes, that is the Transcontinental Railroad, and this is where it went up and over the Rocky Mountains. It began its journey up the mountain, and it was so fortuitous to have this narrow little sliver of land that is referred to as the Gangplank of this formation that lapped on, as we refer to it, that came up along the side of the mountain, onto the flank of the mountain, that just provided a nice ramp all the way up. Isn't that amazing?
The tan area is the top of the alluvium that at one time covered the entire area except for the higher peaks of the mountains. Erosion stripped it back from the mountains a few miles except for the Gangplank, which the Transcontinental Railroad traverses. This allowed trains to cross the Continental Divide further west. The red segment on this map is the path of the Transcontinental Railroad, and the yellow segment is a pre-existing railroad along with others that network the eastern states. Abraham Lincoln signed the Pacific Railroad Act on July 1, 1862, and construction began the following year with the Union Pacific Railroad starting in Omaha, Nebraska, building tracks westward, while the Central Pacific started in Sacramento, California, building eastward. They met each other at Promontory Summit in Utah, and the last spike was driven on May 10, 1869. It was 1,911 miles long. What an accomplishment! Travel from coast to coast now only took 1 week versus the prior 6 months or more. The first transcontinental highway for automobiles, named the Lincoln Highway, went up through the Gangplank and was dedicated in 1913. Looking up the Gangplank towards the mountains, we see Interstate 80, which opened in 1969, replacing the Lincoln Highway.
And I'm also right here with this granite at Vitavu. Really neat place to explore for those of you that haven't been here. This is just granite that looks just like the granite we saw in all the little pebbles and the larger class and even some of the boulders that we saw earlier. And this is where it was being eroded down into the Great Plains, this granite, and other types of rocks as well. The Anorthosite, the dark rock, which came from further north. So now we can see the source of this material that we've been examining. We know that it was quite important because it provided the pathway for the Transcontinental Railroad. Now, I know. You're thinking, well, Myron, that is pretty unbelievable. That's pretty cool. And I'm telling you, there's a lot more to come. This is just part of the story. It's probably less than half. Let's find out why this is even more important in my view in another way, a very different way.
It's time to go east out into the high plains and learn how this great apron of clastics impacts us in 3 more major ways. Driving down Interstate 80 into western Nebraska and turning north into a sparsely populated region, I reflect on what the landscape looked like during Miocene time and how interesting it is today.
Well, I'm going to throw another curveball at you. I'm supposing that you're starting to understand I enjoy doing this, and I'm 150 miles east of the Gangplank in western Nebraska, by this wonderful lake here, teeming with wildlife, lots of birds. In this small area of a few lakes, there's some 15,000 birds that migrate through here on a daily basis during their peak migration period in October and November. And it turns out that in western Nebraska, there's some 2,000 of these lakes. That's pretty hard to get your head around. But you know, there's something kind of odd about them. And that is, there are no interconnecting rivers or creeks. You can't find a creek coming in or exiting. There's no drainage. And usually you might think, well, that would be a dead pool, a dead lake. And you're right. But there are times they're not, in special conditions. And we have those here. And I'll bet you're starting to suspect they're tied to this wonderful layer of rock I've been talking about. And you'd be right.
A look from above can assist us in understanding these lakes. The surrounding topography is very interesting. Does it remind you of anything? Using Google Earth, let's go to another lake and examine the terrain. This landscape looks very familiar to me. I know a place that has a similar look to it. This is a portion of the Rubicali, or empty quarter desert of Saudi Arabia. What an unbelievably beautiful Aeolian dune field we see here. The flat low areas between the dunes is referred to as the interdune area. With this knowledge, it's clear that all the small lakes, ponds, and green grasses lie in many of the inner dunes of the Great Dune Field of Nebraska, which is also known as the Nebraska Sandhills. What a wonderful journey we're on! Using some simple observations, we now know that a large area of western Nebraska is covered by an ancient stabilized dune field. At 20,000 square miles of dunes, it is the largest in the Western Hemisphere. They've been active many times over the last 13,000 years.
Now that we know about this huge dune field in western Nebraska, I wanted to bring out the old whiteboard here and show you a cross-section so we can understand how the lakes work in the inner dune areas. So here are the Rocky Mountains. The apron of material that's shedding off the mountains, that onlaps the mountains here, out into the Great Plains. This is depicted here in the blue. And what is the name of that layer, by the way? Well, it's the Ogallala Formation. And I know many of you are going to go, I know the Ogallala. I think it's the Ogallala Aquifer, and you're right. It's more commonly referred to as the Ogallala Aquifer because it's so important as an aquifer. So here we have this aquifer that's full of water in many areas. So let me sketch a couple dunes here. Obviously not to scale here, I'll make them gigantic here. A dune here, another one here, and one more. Now, in the interdune areas, if this aquifer is full of water right to the top of the aquifer, so the dunes are just sitting right on top of the Ogallala, by the way, as shown here. If that water table's right here, it forms a lake right between these dunes because those are the lowest areas. And hence you have the lakes between the dunes. Now, as far as them not having drainage and being fresh and nice, well, if you think about it, we know the water is charging through rainfall and rivers and everything and moving out into the basin. They've actually measured it. It's about a foot a day. So if you imagine a foot of water moving through here a day, you're replenishing that lake continually, and hence you have this wonderful, clean, pure water in all these lakes. Just a wonderful setup.
The dunes themselves are very important as they provide the environment necessary to have these wetlands. Furthermore, due to their topographic nature, they are too steep to farm and haven't been plowed. They are considered to be the best place to see unscathed Great Plains. By the way, where do you think this huge volume of sand came from? Yep, it's the Ogallala. Fascinating, isn't it?
I'm some 190 miles east of the Gangplank in a small community named Ogallala, Nebraska. Now, of course, that's where the name of the formation came from that N.H. Darton gave it in 1898. He did a lot of the geology in Wyoming too, up in my part of the world, so boy, he sure got around back in the day. The Ogallala that I have here behind me, this is just a small part of it. It's up to 600 feet thick or so in this area. It varies. In parts of Nebraska, it's over 1,000 feet. But here, it's a fine-grained sandstone or a medium sandstone. So the particles are much finer in general.
This typical exposure of the Ogallala in the region is composed of mostly unconsolidated sand, pebbles, and some limited cobble-sized material, just what you would expect as you move further away from the mountainous source.
Well, at any rate, we've focused on the great apron of material shedding off of Wyoming highlands down to the east in Nebraska now. But in reality, that same process occurred all along the Rocky Mountains to the south, shedding a great apron of material through alluvial fans and rivers, and all of it coalesced to make this very large area of the Ogallala Formation, more commonly known as the Ogallala Aquifer. And as you might imagine, that Ogallala Aquifer has had a massive impact on agriculture in the Midwest.
The Ogallala is in 8 states and covers 174,000 square miles. It has a larger volume of water than any other aquifer in the world. It's enough water to cover the entire United States with 1.5 feet of water. It's really hard to get your head around this. It provides water for 1/3 of all irrigated land in the U.S., which produces about 1/5 of all agriculture in the U.S., and is worth about $35 billion annually. A lot of water is pumped out of this aquifer. It's equivalent to about 1.5 times the flow of the Colorado River. Unfortunately, this results in significant depletion in the southern parts of the aquifer. The recharge by rain and rivers just can't keep up. Let's take a look at this depletion map from the United States Geological Survey. It's color-coded according to the number of feet the water table has fallen or risen. Slowly scrolling to the top of the map, we can clearly see the impact of over-withdrawal. The one interesting exception is most of Nebraska, where it shows little impact or even areas of rising water tables, which surprises me. I saw first-hand evidence of the rising water tables. There were lots of drowned and dead cottonwood trees along some of the lakes, like this one.
Well, I guess we've learned in this case that, as the saying goes, you can't judge a book by its cover. This ordinary rock is really something else, isn't it? Well, I hope you've enjoyed this video, and thank you for watching.